Up to now, all the forces that we've been talking about have been point forces or moments, but what I'd like to do now is talk a little bit more about loads in a more realistic setting, and I'd like to introduce the concept of distributed loads. So let's go ahead and consider somebody standing on the ground, and there's a gravitational field that's pulling them down, and so there's a force acting between the person and the ground here. And that force that exists between, say, the shoes of the person and the ground, that's actually what's known as a distributed force. So the reality of the loading is that I have some load and it's distributed per unit area underneath the person. Okay. Now, in the analyses that we've been doing so far, we would have considered this load through an idealization. We would have idealized it as a set of two point forces acting in the region someplace underneath the person's feet. Okay, so what we have over here in this picture over here, we have the reality of the situation, and over here we have sort of an idealization of this system. The two are connected to each other, and the way they're connected to each other is that case one, in other words, the distributed load case, is connected to the point force load case, which I've labeled here too, in that the two situations should be equivalent to each other. So 1 and 2, the two different force systems, should have the same net resultant force and the same net resultant moment. And we often use the idealization of the distributed loads as point forces because it facilitates analysis and makes it a little bit simpler. So, and we'll see that as we move forward when we look at some actual applications here. But I just want to sort of set the stage here is that most loads are distributed over some area, and we convert those then into point forces, and the way we do the conversion is we make sure that the point force case has the same net resultant force and the same net resultant moment. Now, distributed loads themselves, they can come in a couple of different varieties. They can come per unit length, per unit area, or per unit volume. And let's just look at two very simple examples here. So an example of a per unit area loading would be the load that a mass of water applies to the face of a dam. So over here I have a dam, and there's the face of the dam, and we have this mass of water here that's pushing on the face of the dam. And on the face of the dam we actually have a force per unit area, and it's given to us by this formula. You can derive this from sort of elementary fluid mechanics. It's the density of the water times the gravitational constant, and then it's multiplied by y, which is the coordinate in the downward direction. So the load on the face of the dam increases linearly as we go down the face of the dam, and it points in the negative x direction according to the coordinate system that I've introduced in the drawing. So this is an example of a force per unit area. So if we were trying to analyze the dam, maybe we'd be interested in replacing this distributed load over the face of the dam by some kind of simpler force system, maybe a point force acting in the middle of the face of the dam is what we would actually do. A second example of a distributed load is loads per unit volume, and the number one example of that are gravity loads. So if we have gravity acting on an object, so we have a body omega here, we have a gravitational force, in this case in the z direction, and this induces a force per unit volume in the body, and the relationship is rho g, so the density of the body times the gravitational constant, and it acts in the z direction. So this is a second example of a distributed load. So there are lots of them. Electromagnetic forces come per unit volume also, and they're quite for a wide variety of them, but gravity is the one that we are most used to.